we did last time. What we did was that we quickly went through first of all, what is the flat space? Five-dimensional supergeometries look like. And then we learned that almost everything is controlled by a thing called a superpotential. The pre-potential. And also, what we did next was that we learned that in order to put this theory onto a curved space, we need to first couple the theory to supergravity and then try to freeze the gravity multiplets. In doing so, what we need is the following. We need and then to freeze gravity, what we need is the killing spinors. And let me remind you what is the killing equation. And then having a pair of solutions with plus and minus, we call that we have 1,1 supersymmetry. And next, we also learned that assuming that there is a pair of such solutions, it gives strong constraints on the geometry. Namely, this would imply that we are on Sasaki Einstein manifolds. So basically, that's what we did last time. So there's still one question to be asked. First of all, assuming that we have a pair of solutions to the killing equation, we get the Sasaki-Einstein manifold. But reversely, if you are given a Sasaki-Einstein manifold at 5D, first of all, is it even a spin manifold? Secondly, if it is there a pair of solutions, at least one pair of solutions to this equation? So, given so for this question, I'll just quote the theorem and I'll not prove it, nor can I prove it. So namely, if n is SE and if H1 is full. So it's a constraint on first homology of this manifold. So if its first homology is portionless, then this manifold is guaranteed to be spin. And then an example would be the following. So we know that S5 is Sasaki-Einstein and all spheres are spin. But there's this manifold, which is this, the RP5 projective space, which is this S5 mod out by Z2. And since Z2 acts by isometry, if S5 were Sasaki-Einstein, so will be RP5. But this manifold has no spin structure because the second Stiefel-Whitney class is not zero, which obstructs the spin structure. Secondly, now we know that, all of the Sasaki-Einstein manifolds will be actually will be actually simply connected. So we are well under the jurisdiction of this theorem. So we don't need to worry about the existence of spin structures. So the next question is that does it emit a pair of solutions to this equation? For this, let me just sketch. There's a constructive way of constructing the solution when the manifold is simply connected, but I'll not go through too much detail. Just tell you sort of what does it look like. So so to do this, we'll actually just utilize the geometry that's offered to us by the Sasaki-Einstein manifold. Let me just briefly recall that locally the structure would look like this. So the final manifold has got a vector field, vanishing vector field, which is denoted as R because it's the Reed vector field. And then let me remind you that it is a Killing vector field of constant length 1. And then there's this horizontal, there's this transverse plane to this vector field. And then on this transverse plane, there's a complex structure acting. And when the manifold is Sasaki-Einstein, this is actually a Kähler structure. So now, let's just build a spin bundle. And then to build this spin bundle, what we do is that, first of all, we can consider the forms which are horizontal forms, namely these are forms such that so if chi is a horizontal form, that just means it is annihilated if you contract it. It is zero if you contract it with the Riemann vector field. So this will be the horizontal forms. So they're sort of like the forms that live in this plane. Secondly, we can use this complex structure to decompose the forms into holomorphic and anti-holomorphic components. Let's consider the following bundle equal to now, because the manifold is 5 dimensional, so the transverse plane is 4 dimensional, and then so I can only run from 0 to 2. And in fact, if you just do some counting, you will realize that the rank of this bundle is 4. Rank W is 4, which is the correct dimension for the representation, for the smallest representation of the spin structure 5D. And then, so how does the gamma matrices act? Suppose that I have. Let me just locally choose coordinates psi I and psi I bar. Then the gamma matrices will just act like this. So gamma I bar acting on, let's say, on W is equal to so one of the gamma matrices will act like raising operators, which means that it multiplies the form by another b psi I, while the other one will act as if it's an annihilation operator. It eats one anti-holomorphic index, while this and then this particular gamma matrix will just act as multiplication of the degree -1 to the degree, and then this operator will become important later. Let me just give it a name. So in fact, what we have is that we define this operator -1 or minus r. We call this the chirality operator because the r squared has length 1. So this matrix has plus or squares to 1. So it has plus or minus 1. Eigenvalue, and this matrix will split the spin bundle into plus and minus chirality subbundles, and in fact, the plus chirality corresponds to those forms which are of even degree, so 0 and 2. The minus ones will be degree 1. So, with this spin representation, the spin connection is actually almost the same as the Levi-Civita connection, with some shifts. Let me not give you the precise formula, but the message was that in this formalism, this Killing, you can always construct a solution to the Killing equation. In fact, for the one with minus sign.
Jian, sorry, one basic thing. You start from a Sasaki-Einstein manifold, and how you get the Riemann vector field? Is it something?
It's built in. It's
out of the.
It's a part of the definition
of the Sasaki-Einstein.
Right. It's maybe I should have said. So a Sasaki-Einstein manifold is a metric contact manifold. So it's contact, which means it has got a Riemann vector plus the fact that its cone is scalar. And if it's again Einstein, then that means its cone is Calabi-R. But I reserve this for the last part of the talk because in the last part I hope to deal with Sasaki-Einstein more systematically.
What you just said though almost applies to a theorem over here. Because if you know that the cone is spin, then it follows that the Sasaki-Einstein spin.
Right. Yeah. In fact, so I'm just constructing a solution. So this is completely general, and
I'm trying to explain to you why your theorem is true. The theorem that said that M is spin if H1 times A is torsionless. I think you can deduce that from the same statement about the cone.
well, I think this one will have the cone divided by Z2.
That one, the torsionless hypothesis isn't true. Suppose for simplicity the H1 times A is 0. What you've told us is that the cone on a Sasaki-Einstein space is locally an SU3 element.
Right.
So if there's no torsion, it's also globally. If it's simply connected, it's also globally.
Right.
What it means to be locally SU3 element is that there's a covariantly constant spinner that's unique possibly up to a phase.
Right. Okay.
So the reason that this H1 comes in is that you can worry that a parallel transport around the loop, it would transform by phase, which is what actually happens in the S5 over Z2 example.
Okay. So meaning, okay.
So if, for simplicity, if M is actually simply connected, there's no possibility of such a phase. So saying that the cone is locally Claviel implies that the cone is really Claviel.
Okay.
A Claviel manifold is spin. And if the cone on something is spin, then that something is also spin. Kind of trivial.
Yeah. Okay. So in fact, yeah, the construction of the solution to the Killing spinner is exactly along the line that we just heard. So let me just say that the solution can be constructed in this way, and it's actually quite simple. One solution with the minus sign here is actually the 0 form. In fact, it's equal to 1 in this language. And the second one is a section of the 0,2 form. And then the fact that such a non-vanishing section to this envelope exists is guaranteed by the Sasaki-Einstein condition plus simply connectedness. So for S5, you can actually explicitly write down what is this one, but let me not go through the details. But one thing I do want to point out is that both solutions, they're both even forms, and hence they will have plus chirality. So this will come back to us later. So this is so much I want to say about Killing spinners. Next, we'll get back to the localization. So before I move on, any questions?
What can you say if it's not torsionless? What can you say if it's not torsionless?
What can I say if it's not torsionless?
It's not spin.
Yeah, this guy is not
Then we have
spin.
to look more closely.
Okay. So, if there are no further questions, I think at least for once in this lecture, I'll write down supersymmetry transformation on the curved space on this. So, this is for vector. Let me remind you that this is the gauge field, this is the gaugino. So the version I'm writing down is actually an off-shell version. The off-shell version is available. It's just a little longer, so I thought I'd better not write it. Now this is for the vector, and I realized that last lecture I didn't even tell you what the hyper looked like. So I need to repair this omission here. So the hyper consists of a scalar, which is iso doublet, and then A is the index, which runs from to n, and then there's a fermion, and also with the same index. So for hyper, the biggest possible gauge group will be at SP to n, And then we will just choose a subgroup of this as our gauge group. So in particular, I'll just choose SUN as a gauge group. And then this scalar will satisfy the following constraints. So when epsilon ij is the invariant tensor for SU2 for the idle spin, omega AB is the invariant tensor for the SP2n. So in particular, if you want to look at it, we can look at the scalar in a slightly different way. So we can write it as a doublet as a pair of scalars. If you write it like this, then if this one transforms in the fundamental of SUN, this one will transform in the anti-fundamental of the SUN. So this is probably more familiar to most of you. Okay. And then with this field content, let me just write the supersymmetric transformation once. And you will see that in both supersymmetry transformation rules, there are corrections which are suppressed by the radius of the sphere. So the flat space will be just you remove these terms. Now, so why do we go through all this trouble? What good does it do to us when we want to localize the theory? So next, I'll just go through the general story of localization using a toy model, and the extent of the localization theory we're going to use is certainly not rocket science, as you will see in the following toy model. The toy model is the following. Consider a manifold, finite dimensional manifold, and then consider its, let me write it down first. So this notation means that, let's consider its tangent bundle, and then this time means that you reverse the statistics for the fiber, so the fiber coordinate becomes an odd coordinate. So now let me call xi the coordinate for the base for the manifold itself, and then psi I is the coordinate for the fiber, and then by all accounts we can just think of psi I as if it's E at I. In fact, functions are just different. So functions on this supermanifold are just differential forms on M. And also the integration over the supermanifold is just the usual integration of differential forms on M. Now, consider the following differential. Let me let R be a vector field. Vector field of M, such that it is killing. So assuming that there's a metric, of course. Assuming that R is a killing vector field. And consider this following differential. So actually, if you write everything in terms of differential forms, delta is just the following thing. So it consists of one part, which is the ramp differential. The other part is the contraction with the vector field R. And it's easy to check that delta squared is not 0, but it's equal to the Lie derivative along the R direction. So let's try to integrate a form, consider a form. So as I was saying that differential forms can be thought of as functions on this supermanifold. So consider a form such that 0 and we want to integrate it. Now, let's consider the following integral. Where so V is just some unspecified object which is odd, such that delta, for now, such that delta squared of V is equal to 0. First of all, it's obvious that if you set t equal to 0, you remove this term, you get the original integral back. Now let's look at what happens if we change t. Let's differentiate with respect to t here. So you just pull down a factor of delta v. Now we can integrate, we can pull this down because of our assumption that both omega and delta v is annihilated by delta. We can pull this delta to let it act on the whole thing. And then this is going to vanish by using the Stokes theorem. So by the simple manipulation, we see that this object is independent of t. So we can evaluate it for large t and see what happens.
It's independent of t if t isn't 0.
Right.
It doesn't really converge if trying to succeed, so.
Oh, no, actually, let's suppose that this thing itself is
Oh, if it already converged, then
yeah,
it's actually independent.
yeah, right, yeah.
Are there any assumptions about R? Maybe it has no zeros or something like that?
Yeah, it will have a 0. It will be important to have a 0. This one. So, I, t very big. Now, let's suppose that we have made a wise choice of delta v. Namely, delta v, well, since v is odd, delta v will be even. Let's suppose that it is positive definite, and then because this factor gets really big, so the integral will be dominated by the critical points of this function. So then what we'll do next is that we just, the integral is really simple now, because we just go to one of each one of these critical points and then evaluate this form at that point. And as for this one, we just need to integrate over small fluctuations around this critical point, which is going to give us the determinantal factor. So let me write it down here. Suppose well, let me just assume that the critical point is given by x equal to 0. Suppose that at the critical point, delta v has the following small expansion. Where G is a metric and this is some antisymmetric matrix. Now, integrating all the small fluctuations around this critical point will just give us the following determinant factor. So it's the square root of determinant, sorry, t and t. The square root of the determinant of the metric and then the Parthian of omega. And then a simple dimension counting will tell you that actually the power of t is the same both sides, so we can remove it. And then the rest of the term, namely the further expansion, will give us determinantal factors which will be suppressed by large t. So if we consider t go to infinity, that's all you get. And then you go through this procedure for all critical points. That will be the full answer of the integral. And still, at each point, you have to compute such ratio of determinants. But in fact, this determinant is, roughly speaking, independent of the choice of v. The reason is that so far we have not used the condition. We have not made use of this condition so much. So if you look at what's the implication of this equation when you do extension like this, you will realize that you will have a relation between this matrix and this matrix, which is the following. That's the critical point. Oh, by the way, let me just mention that the critical point of this this delta V will necessarily imply that it's also the zero of this vector field. Now, using this condition, it implies that at the critical point, there's the following relationship between these two matrices, namely.
Is that automatically symmetric?
Yes, because you need to use the condition that. You need to use the condition that the delta squared V is equal to 0, so there are some sort of relations you can derive, and also the fact that I assumed earlier R is killing. So, namely, the ratio of determinants is actually up to an irrelevant factor always equal to this thing.
Sorry, where did you assume something about R?
R is a killing.
But there is, I thought it was any vector.
Oh, killing vector.
So M is M asymmetric?
This one?
Yes.
M is just a manifold.
So it's Keating with respect to what?
A metric of this manifold.
Right, so it has metric.
Yeah, asymmetric. Sorry, I thought you said asymmetric.
No, sorry, it has metric.
Okay. Okay, so this ratio of determinants is always equal to the following thing. So let me just summarize what happens. So to do the localization, you need to make a wise choice of this V, which will determine for you what are the critical points. But once that is done, the determinant factor to be computed is always given by the same read vector the same killing vector that you have chosen. So this is basically the procedure of localization. So how do we apply this? Before I move on, any questions? So we're going to apply this procedure to our story. Namely, we're going to use our killing spinner to single out a particular supercharge and then rearrange all of our fields into this type, so that to make them look like that, and then apply essentially exactly the same analogy here to compute the path integral. Right. Okay. Back to our field theory. So in general, we know that two supersymmetry transformation entity to the following. Translation plus rotation plus R rotation plus what else? Gauge transformation plus dilatation. And then, now that we have chosen our supercharge by using the killing spinner, so what we get in fact is that delta squared. Let me just put a sign here to remind ourselves that it's the supercharge chosen by the killing spinner is equal to, well, translation is the same, plus rotation, and then R rotation plus gauge. However, the dilatation goes away. The reason for that is because the dilatation will be done with the following, has this following parameter, the divergence of the reed. But remember that the reed is actually killing, so the divergence vanishes, so the dilatation goes away. And furthermore, the translation plus rotation combines into something really nice, actually. So translation plus rotation combines into two cases. Lie derivative if the field in question is scalar or form. And then following, if the field in question is a scalar. So what is this? So Lie derivative, I think it's a familiar object. But what is this thing? It's called the spinor Lie derivative in the literature. And in contrast to the usual Lie derivative, it can only be written down, or it can be written down for any vector field, but it will only have nice properties for killing vector fields. Namely, suppose, let me just give you the definition of this thing. Suppose X is killing a vector field, then now this is equal to so it acts on the spinors just very much the way Lie derivative acts on the differential forms. It has the following nice property. Just like the Lie derivative. And also the following. Namely, it commutes with the spin derivative. So this is a very good property. Oh yeah, x, y both killing. So if you drop, you can also write down this thing for any vector field, but if you drop the killing condition, you will get the curvature term here. So this condition is really good. Let me just make a remark here. Because since it commutes with the spin derivative, so if you let this operator act on a killing spinor, it will produce for you a new killing spinor. So in this way, if you are able to find isometries from a geometry, and you can use this isometry to construct new killing spinors so as to be able to enlarge the supersymmetry algebra. It sounds useful, but actually not as useful, because it turns out that in 5 dimensions, the only manifold on which this enlargement works is S5. For all of the other Sasaki-Einstein manifolds, all of the isometry, if you construct the corresponding spinor Lie derivative, will annihilate the pair of killing spinors you already have. So, in other words, in 5 dimensions, the only So S5 has got more supersymmetry than this 1, 1. Now, so we still have a little more unpleasantry to go through before we can do something really interesting. So now I said that we need to optimize our fields into this sort of this relation, into this sort of equivalent differential type of relation. So So what we're going to do is the following. So for the vector, we'll combine the killing spinner with the KG node, because it kind of pays off to consider isospin invariant object. So let me just write my formula. In fact, let me. So you can combine.
It's lambda, they're not psi, right? You're talking about psi.
Yeah, okay. So when you combine two spinors, the spinor bilinears can be decomposed as differential forms.
So it's the second line, I think they say probably.
Yeah, right. Right. Okay. So the spinor bilinears can be combined and then re-decomposed into differential forms. And then here what we got is actually a one form and a two form. And this two form chi satisfies the following relation, namely it's 0, so it's horizontal, meaning it's a horizontal form. Secondly, and more importantly, it satisfies some kind of duality relation. And you might wonder what this duality relation means in finite dimension. It is the following. So let me define a duality relation by means of the Reed vector field. Namely, what you do is you just first take the Hodge tool and then contract again with the Reed vector. So if you start out from a 2 form, from here you get a 3 form, and you get a 2 form back. And then this chi is actually self-dual under this duality relation. So I will just write it as the following: 2 plus. And then you can do it as an exercise to show that. So you have a 1 form plus a horizontal self-dual 2 form. Count the number of degrees of freedom, and you will realize that it's got the same degrees of freedom as a spinor in 5 dimension. And in fact, this change of variable is invertible, so it's really a change of variable. So with this rewriting, the pseudosymmetry algebra can be written in a very compact form, and I realize that time is not on my side, so let me just write it schematically. Let me explain the notation. First of all, H is a field that we have not seen yet. That's because H actually comes from the auxiliary field in the vector multiplet, but I didn't write the off-shell version of the pseudo transformation, but well, H, that's where H is from. And then phi here, which is, so this means that the H transformation using phi is a parameter, and phi is the following combination. So phi is this combination, and then the other phi is the only augment out, namely. Okay, so this, if you just look at this for a moment, you realize that it has got exactly the same pattern of equivalent differential that I just erased. And also you can check that delta squared is always equal to translation plus H transformation on all of the fields except phi. While on phi, this goes to 0. And then I'll come back to comment on what to do with this later. But so the moral of the story is the same. We now managed to rearrange our fields into the pattern earlier, that's delta x equal to psi and delta psi equal to a vector field. So the next step in the localization procedure is the following. We need to add to the path integral a cleverly chosen v such that delta v has got is positive definite and has got nice properties, and there really is no explanation for how you find it. You just poke around until you find something that works. So what is it? Okay, so let me just write down our choice, and then actually I'll only write down what's its bosonic part. And then that's going to lead us to some interesting discussion about localization locus and hence the compact instantons. Plus stuff that doesn't concern me. So let me explain the notation again. F is the field strength. And then the subscript H means that I take its horizontal component. And then 2 plus means that I take its self-dual component. So the self-duality is using the self-duality condition that is here. Okay, so now let's just analyze what is its critical point. Well, it's actually, because it's a perfect square, so the critical points are easy. And
Can I just ask you something?
yeah.
Yeah. So you were saying that this relation between the Pfaffian and the determinant square root of J was essentially independent of, I think you said it's essentially independent of your choice of localization. Okay, so that means that you're free to choose locally essentially. But what are you guided by when you write this particular?
So I want to choose a v such that delta v is positive definite, so that it has enough convergence power to converge the path integral in a way. I mean, right now it's a perfect square, so.
But there must be lots of choices.
Yeah, I mean, it's hard for me to say what is the best choice. I mean, as I said, we just poke around until you find something that works.
You can't, what restricts it is that it's supposed to be delta of something.
Yeah.
So something has to be fermionic. So part of delta will be what a bosonic expression of the fermion transforms into. If you want to get a sum of squares, V basically has to be a sum of fermions times whatever the fermions transform into.
It is, in fact, more restrictive than I thought.
Yes. Well, for example, you could add a derivative of the fermion times the derivative of what the fermion transforms into. Then that would also transform into a square, namely the square of the derivative of what the fermion transforms into. But it would just be a more complicated. Given what you can try to do, there's kind of minimal.
Yeah.
Okay, so this is the set of equations that is going to give us the critical points, or we call it the localization locus. And this will be the last subject of this lecture, I think. So there's not much to be said about this equation. It just says that sigma is a covariantly constant scalar. And these two came to be called compact instantons. In the sense that, so this condition says that, let's remind ourselves the structure of the five-dimensional manifold. So this says that the field strength has no lag along the read direction, and then if you restrict everything down to the horizontal plane, it is self-rule. So, okay. We can try to analyze this equation preliminarily. So I'll do it in two cases. One is that when our manifold read vector field, so case one, when the read vector field has closed orbits everywhere, so namely it will look like this. So the phi manifold is basically a U1 vibration over base. For example, you just look at S5, like the example last time, which is a U1 vibration over CP2. And then the read is really just the circle direction. Now, because of this nice structure, in the sense that you can take a reduction against this U1 direction and then push everything down to the base CP2, actually what you get by reducing this set of equations, what you get is the following. So now we are on CP2 now. It's F2 plus equal to so rho is a scalar which basically comes from the vertical component of the gauge field, because under reduction this becomes a scalar. So this equation is kind of a perturbed Donaldson equation, namely if this side has been 0, then it says that the field strength is self to, okay, that's the Donaldson equation. Here it's slightly perturbed by a covariantly constant scalar. So for this particular case, this particular simple geometry, we can show that for SU2A2 or SU2, this set of equation is in one-to-one correspondence with just the usual instantons on CP2. So in the sense that we get nothing new, so we get so in this regular case, you can say that we get nothing new from considering this more general set of equations. The next case irregular read, in a sense that the read vector field does not have closed orbits except at a few points. So, a few points. So the rest of the read orbit does not close. So we have no conclusive results for this case, but it would seem that as soon as the read vector field does not have closed orbit, you almost destroy almost all of the contact instantons, and what you have got left over are just a few instantons which has got a curvature, a delta function supported along precisely where the closed read orbits are. So, for example, even for the case of S5, you can slightly deform the read to make it irregular, and then you are left with only generically 3 closed orbits, and then you are left with 3 possible sort of point-like instantons in this case. And then we don't have a conclusive proof for this, but with some kind of semi-sloppy argument, we can show that this is always the case. But I think this really is the way to compute the instanton partition function, namely, even when you are in a regular case, what you should do is to slightly perturb the geometry so as to localize everything to the read orbits and then compute everything so that you can go to the local neighborhood of these closed read orbits, and then the local geometry will always look like C2 cross circle. So I just threw out this to sort of elicit more research. Okay, so this is what I want to talk about for the well, once this analysis is done, well, this just says that sigma is a covariantly constant scalar. Now, in the actual calculation, because we don't yet know how to do instantons rigorously, so let us just specialize, or rather retreat to the case of zero instanton. So this case, what at least we can do, namely, the localization locus will be given by simply the gauge field equal to 0. Okay, and in this case, covariant constants is as constant, sigma being a constant, i.e. sigma. So for A equal to 0, sigma is equal to sigma 0, which is a constant inside of the algebra. Whoops. Okay, so in a sense that this constant inside of the algebra will be the modular for the Coulomb branch, and then we'll eventually, what we'll do next is that we'll go to this localization locus, integrate over the small fluctuations, and then also integrate over the modular. So that's what we're going to do for the vector. Well, for the hypers, the story is simpler. Any questions on this? For the hyper is simpler, so we just combine so in this case we combine the Killing spinner not with the fermion but with the scalar, because remember that we would like to consider always isol spin singulets. And then also recall that I made a remark earlier that all of the two Killing spinners have plus chirality, which means that if this new spinner field, which is a combination of these two, has plus chirality. And then the supersymmetry transformation simply reads the following. Sorry that this is a small sign, which is not the same as the sign in the vector multiplet. And then I put the plus here. The plus means that you take the plus chirality component. Let me not write. Okay, sorry. I need the rest. So plus and minus simply means the plus and minus chirality component. Now notice that what features in this supersymmetry transformation is that delta squared is given by the same gauge transformation as before, but now the Lie derivative gets replaced with the spinner Lie derivative. Because now our fields remain spinners. So we have to do the same thing, namely find a clever V and then look for what are the critical points. But it turns out that the story is easy, namely the critical points. It can be shown that the critical points are just everybody equal to 0, so Q and psi and everything equal to 0. So in a sense that, at least when we consider only the Coulomb branch, the hyper is rather simple. So this is as much as I want to say about the localization locus. What we're going to do next is essentially the second step of the localization, namely go to the fixed point, go to the critical point and compute the determinant of either this operator or the operator for the vector, which is that you remove x here. Okay, so any questions? So I think I'll have enough time to sketch for you what we're going to do, and then I'll finish the calculation in the next lecture. So, You might have noticed that so far I've been silent about the problem of gauge fixing because clearly we're not going to integrate over configurations which are gauge equivalent. And also, you will remember that this relation with or without S is not true for all fields. There's a particular field, namely the phi that generates a gauge transformation, that is different. It doesn't follow the same pattern as the rest of the fields do. Now, these two questions, namely the gauge fixing and then this guy, can be fixed with one stroke, namely you just introduce the ghost sector. So let me tell you what will be achieved by the ghost sector, and the details will okay. I'll provide the details in private if you are interested. So the ghost sector will come with its own VRC, the usual VRC differential which squares to 0. And what you're going to do is that you're going to combine the differential we already have with that of the VRC differential such that let me call it new combined differential delta twiddle, such that delta twiddle squared is equal to L R with or without S, depending on if you're working with a vector multiplet or hypermultiplet plus. Now the gauge transformation in this case is no longer generated by this field, but rather by sigma 0. Recall that sigma 0 is the moduli for the scalar field sigma. So let me just briefly explain. So you might ask two questions. First of all, why is it even possible? Secondly, if it is possible, what really happened? So let me try to sketch or attempt an answer to the second question. And in fact, I will not write anything. So let's put aside this operator for now because it's sort of familiar with it. So this operator should remind you of the equivalent differential in the Cartan model for equivalent cohomology. And so what you do is that let's say on a manifold you have a group G acting on a manifold. Now consider differential forms on M, but now you enlarge it with the Lie algebra G, and then you can define the differential delta, which is then we call it Cartan. It's equal to the usual differential plus. So let EA be the basis of G, the algebra, and then XA be so choose the basis for the algebra and XA the vector field. So you can define the following Cartan differential as the combination of the RAM plus, so this guy is the algebra value and then contraction with the following vector field. Now it's easy to check that the square of, delta. The square of delta is not 0, but given by the following action of the group. So it's exactly what's happening here. Now, even though this does not square to 0, eventually for the equivalence differential we'll consider the invariant elements of this combination. So in the sense that this part descends to 0. Now, there's an equivalent model which is the Weyl model. In the sense that you enlarge enlarge the differential forms not only with an even element of the algebra, but also an odd element. And then the differential for the veil is, so CA is this guy because it's odd, so it's odd. And then, okay, I need to write down the differential also on. So it's easy to check that the outer veil does square to 0, and also this relation should remind you the relation between that of the connection and the curvature. So if you think of C as some kind of curvature connection, then phi is a connection, and indeed C and phi are usually called the universal connection and curvature. So what happened here, namely when we introduced the ghost, is exactly to pass from the Cartan differential to the veil differential, from the Cartan model to the veil model. And also there's one thing I need to mention, that so far we're suppressing any discussion on the ghost to 0 modes. So if you also treat the 0 modes for the ghost carefully, what you will get is exactly this following relation. So if you ignore the ghost to 0 mode, this part will be missing. But if you consider that carefully, then there will be this part left over. So now we have a much better situation, namely we not only solved the gauge fixing problem, but also have a much better operator for which we will compute the determinants, and that's going to be the task of the next lecture. Thank you.
Can you just remind us what these equivariant cohomologies are?
Okay, so in a sense that this is a model. Okay. So this is a model for the cohomology of this space. I don't know if I should go through that. Okay. So this is commonly known as MG. So in a sense, you can pretend that this is that, but this behaves much better than the quotient. So C and phi are sort of generators of the differential forms on this space. So you go ahead and consider its invariant combination, or in this case, the basic combination, and then you compute this cohomology, and that's the cohomology of this thing.
Questions? So could you say again what is your conjecture for contact instantons when the closed orbits are isolated?
So our conjecture is the following. So generically, in fact, for a contact manifold, the read vector does not have closed orbit everywhere, but it will have usually some sporadic closed orbits here and there. Now our conjecture is that in this generic case, the solution to the contact instanton equation has no regular solution except those whose curvature is the delta function supported along these closed loops. So these are sort of the point-like objects.
So singular solutions here.
Singular solutions.
I think in proper sense you have to perturb the equation, you will have a parameter and then you will see. So similar situation happens in 3 dimensions when you have a Seiberg-Witten equations, and then you can establish this analytically. Right? So, I mean, we just have a wild guess that this is the same in
Wild guess.
In examples and toric examples, we can see that I think it's very likely to be true. But we believe that presumably it will be true for general contact manifold. But of course, it's a hard analytical work. I mean, that's what Taos did in 3 dimensions. We are not up to this analytical work where you have to write a lot of bounds, etc.
But your contact instanton equation is elliptic.
Yes, I guess so.
Is what? Sorry.
For sure.
Is what?
I actually
Elliptic.
contact instant equation is so.
It's elliptic.
Yeah, I think so.
Yeah, well, I know that Matai checked and he told me it's elliptic.
Okay.
Well,
And-
the conjecturally only makes sense if the answer is yes.
Well, that would, yeah.
Right. Well, I mean, if you look local, I think it's definitely elliptic.
No, elliptic is a local sentence.
Right, so it's elliptic.
Yeah, in the sense that horizontalness tells you that it's sort of elliptic in the vertical direction, and then the rest is more or less.
And somehow, because of also, if you start to think about index, you try to think about virtual dimension of model space, it will be 0. So, I mean, presumably we would
You shouldn't be able to define the virtual quantized space in the virtual dimension unless it's elliptic.
Right, yeah. Assuming it's elliptic, then.
It's
Well, I didn't study this.
After doing the break, we can discuss it.
Other questions? If not, let's thank the speaker. We meet in 30 minutes, so 11:40 according to that, right? Yes. So 11:40 according to that.